In this video, we're going to talk about the difference between these two things that I have been writing thus far in the course for underneath the symbol for a battery, right? I've been writing sometimes V and sometimes this script E. And I've made the statement, probably, it sounds like something I'd say, that these are not exactly the same thing, but we're going to treat them the same thing very, very often. And that's true. So let's unpack this difference. V is going to be what we call, and I should say that this whole conversation is predicated upon whether or not you're doing a problem which cares, right? Some problems, we don't care what the difference is, and maybe that'll make more sense after I explain it. But some problems do care. So this is what's going to be called the terminal voltage. And this is called, usually we say, EMF. Now, I will go ahead and tell you, this chapter in your book is called Electromotive Force, if you're using the same book that I am. Electromotive force. The first thing to know about an electromotive force is that it isn't. It's actually not a force. But here's what happened when people were first learning how to characterize these things. They knew that if they connected this, what we now call a voltage source, if they connected two ends of a wire to that voltage source, that current would flow, charges would flow. So they knew that there was a charge that was sitting still, and I put it in this potential difference, which means I put it in an electric field, right? You don't get a potential difference without an electric field. And they figured out that this charge then moved. So it wasn't moving, and now it is moving. Well, you know, from mechanics, that has to mean there's an acceleration, which means there has to be a force. And in point of fact, there is a force exerted on those charges. That's why they move in the first place. But as it turns out, that's not the best way to characterize, or not the easiest way to characterize charges moving in a circuit. And at the very least, even if it is, what they were talking about when they said the EMF turned out not to be the force, it turned out to be the voltage provided by the battery. And so electromotive force is an older term that we're kind of stuck with, but we don't say it very much. I know I've said it like 10 times in this video. We don't say it very much because we don't like using the word force if there's not a force there. So I will probably just say EMF. Read that to mean voltage. It is a potential difference. But now what's the difference between the EMF of a battery and the terminal voltage? Well, it has to do with the fact that a battery is, in fact, an electrical component. We've talked about capacitors, we've talked about resistors, we've talked about batteries, but we haven't really considered a battery as just a component you put in a circuit. And as it turns out, any component you put in a circuit offers a little bit of electrical resistance. So here's how that works. Let's say that here's my battery. Let's say it's one of these kinds. And I'm going to draw my circuit coming, well, my circuit will be coming through here. So here is where I'm going to, and I think I've done this wrong. This should be the positive, that's okay. This is going to be my battery. Here is where I've drawn my traditional symbol for a battery. But now I'm going to have to take into account the idea that there is a little bit of internal resistance. So in point of fact, this is called the EMF of the battery. This would be like the rating of the battery. If you bought a 9-volt battery, this would be 9 volts. But what you actually see appearing across the terminals is usually a little bit less than the EMF, because this represents some internal resistance, which we usually denote with little r. Of course, this thing is going to be connected to what's called a load. If you don't know that word, that's a terrible looking resistor. But, wow, that's bad. But I have some sort of load resistance here, and you know, it could be 17 things piled into this R. But the idea is I'm using this battery to run some load resistance, and I'm going to use a capital R for that. And so the question is, well, how much does this internal resistance affect the output of the battery? So let's, first of all, let's look inside the battery and recognize that there's some current I flowing out of this battery. This battery has some sort of E and some sort of internal resistance R. So what I can do is calculate a voltage drop across this little resistor. We've seen how to calculate voltage drops, right? So I can calculate, we've seen it in the context of capacitors and resistors. So I can calculate this voltage drop just using Ohm's law. I'm going to write the little r to remind myself that I'm looking at this internal resistance. And so what if this is a drop in voltage, what that's going to result in is if I measure the voltage between this terminal and this terminal of the battery, I don't see the full EMF. I see the EMF minus this voltage drop. And so the terminal voltage can be characterized like this: the EMF of the battery minus IR. Of course, note that's going to change with the current. The current is going to depend on the load voltage. So in general, this term can vary. Furthermore, it doesn't only vary because of the current. It varies because of the internal resistance of the battery. This will actually change as the battery is used and ages. And if you have a rechargeable battery, this definitely changes along the life cycle of the battery, because you never get the battery back exactly to where you started it. This is why your smartphone, which you bought 2 years ago, doesn't hold a charge as long as it used to. This is why any rechargeable batteries you have don't work so well after a couple years. This is why if you're using a normal battery and a flashlight, the light doesn't just burn brightly and then snap off, right, as the battery is dying. The light gets dimmer and dimmer and dimmer. It's because this internal resistance is changing. So in general, the terminal voltage of the battery is pretty variable. Now, let me put this into Ohm's law. And on the left-hand side, let me remind you what Ohm's law is. V is equal to IR. On the left-hand side now, instead of writing just the terminal voltage, let me write this expression: E minus IR is equal to I capital R. All right, so I'm now recognizing that this terminal voltage is a little bit more complicated than what I've been doing. And of course, if I rearrange here, this means that the EMF of the battery is equal to, if I move this over and factor some stuff out, I capital R plus little r. Now, so all I did was I factored out the I, because the same current's running through it all, right? Now, you can see from this, if little r is really small compared to big R, I can just ignore it. What I can do then is I can assume within a reasonable approximation that the terminal voltage of the battery and the EMF of the battery are equal, as long as the internal resistance is very small. In practical life, that turns out to assuming that the battery's reasonably new and that the load voltage is much, much, much bigger than the internal resistance of the battery. Both of those are very good assumptions to make if you're dealing with real-world examples. Of course, there are exceptions, but generally speaking, whether I write the terminal voltage or the EMF, I'm going to assume in most cases that these are the same. Now, of course, if you're doing an internal resistance problem, then you can't assume that they're the same. But most of the problems we do as far as determining equivalent resistance and things like that, just ignore the fact that there's internal resistance. We assume that it's negligible, and we use the EMF and the terminal voltage interchangeably. Just as long as, we're free to do that as long as we realize that it's not exactly the case. But, you know, if I buy a 9-volt battery and I measure the terminal voltage at some point and I find that it's 8.95 volts, right, what am I going to do? Am I going to be persnickety about that? Probably not. I'm probably just say, oh yeah, it's 9 volts, right? Now, if I'm doing really sensitive applications where I have to have exactly 9 volts, then yes, that's going to be a problem and I'm going to have to figure something else out there. But in 99% of real-world applications outside of a laboratory, 8.95 volts is going to do just fine for my 9-volt application, if that makes any sense. So the upshot of this is if you're doing an internal resistance problem, you care about the little r. If you're not, you are free to set the EMF and the terminal voltage equal to the same thing.